we're going to explore the satellite equation, which is simply F equals ma when the acceleration is centripetal acceleration. So we've done this many times already. For instance, remember the car on the inclined ramp going around the turn? Okay, it's going away from you, and so the normal force is upwards, the force of gravity is downwards, and when you add that normal force to the force of gravity, you get mass times acceleration. And this car is accelerating into the center of the circle as it takes off on this frictionless acceleration ramp. The satellite equation is easy to apply to a satellite around the Earth. And so if here's the Earth, and here's a satellite in lower Earth orbit, say lower Earth orbit, LEO, where the radius of the orbit is about the radius of the Earth. These are about 100 miles high, and the radius of the Earth is what, 6,400 kilometers? That's 6,400 kilometer, right? So it's only got one force acting on it, and because the distance is about the radius of the Earth, we could say this is about mg. And it's very simple to say, oh, now we've got mg is equal to mv squared over r. The masses cancel, and we can write the velocity is equal to the square root of rg. That's not hard. Let's check it out. That's 6,400. That's 64, and this is times 10 to the 1, 2, 3, 4, 5 times 10 to the 5th meters times gravity, which is just another 10 meters per second squared. So we can cancel this and make this 10 to the 6th, and this is meters squared per second squared. Oh, we don't like it until we see this in 1/2. So square root of that is meters per second, and the square root of 64 is 8, and the square root of 10 to the 6th is 10 to the 3rd, or 8,000. So that's 8 kilometers per second. So that's how fast these satellites are, like, for instance, the space shuttle in lower Earth orbit. But as we get further away, at a much greater distance to the Earth, we can no longer say that the force is mg. Now the force is m1, m2 over r squared times the gravitational constant, and that's equal to mv squared over r. Okay, so what are we talking about? Let's call this the mass of the satellite. And so we have mass of the satellite, and this would be the mass of the Earth. We can put things in terms of the period, the amount of time it takes this to go around the planet. With the relationship velocity is equal to distance over time. Well, the distance to go all the way around is 2 pi r, and then the time is just the period of revolution. And when we substitute this in to our equation here, we now have mass of the satellite times 4 pi squared r squared over t squared, 4v squared, and then we have this r in the denominator. So on this side, we have the force of gravity, and on this side, we have mass of the satellite times the centripetal acceleration. Okay, we can cancel one of these, and we can rearrange our terms so they look like this. You can see that I canceled the mass of the satellite because the acceleration of the satellite doesn't depend on its own mass. And I rearranged the terms so that the variables, the radius, the distance to the planet, and the amount of time it takes to go around, that ratio is set equal to things that are constant: the mass of the mother planet, g, and just numbers we know. This relationship was founded by Kepler by observations, an astronomer, in looking at the period of the different planets going around the sun, where this was the mass of the sun, this was the distance of the planets to the sun, and this was the period. And so we can see, for instance, if you double the distance of a satellite to the mother planet, the period goes up by more than 2, because this would go up by a factor of 8, and this would be the square root of 8, period would go up. And the reason is because if you double the distance, you double the distance it has to go around the planet, but you also lower the velocity because the gravitational force and the acceleration is less. For example, in lower Earth orbit, as we were talking about, at 8,000 meters per second, it takes about an hour and 40 minutes to go around the Earth. I believe you can go around about 18 times a day. But if we go way out, far away, we can get to a point where it takes a full day to go around, and that would be called geosynchronous orbit. Say geosynchronous orbit. Okay, this is a very special distance because it allows for a satellite to go around the Earth at the same rate it rotates, and therefore when we look up, we see the satellite as not moving. That's where all of our TV and radio satellites are. And so using this ratio, we can compare these two. This at a distance of 1 Earth radius at about 18 times a day. And geosynchronous orbit requires that we go out about to 8 Earth radii in order for the period to go from about an hour 40 to 24 hours.